All right. All right. You're back. You haven't ran away yet. This 1998 AP Calculus AB exam is a little bit of work, a little bit of rigor, but we got this. Okay? We did all of section 1, part A and B, multiple choice. Section 2, there is no part A or B. It is just section 2, all 6 questions. We've done question 1 already. We've done question 2 already. And we are on to question 3, right? The nice thing about this is a graphing calculator is required for some of the problems or part of the problems, and we get to use it. So without wasting any more time, first of all, follow me so you can get notified when videos come out for questions 4, 5, and 6. And also give me a like, because that helps me live longer. I live on the souls of young people. I'm hoping to live forever. And that can only happen when you like the video, ring the bell. Do what you need to do, kids. Number 3 reads, oh boy. You guys know how I feel about graphs and charts. Love me some photos and pictures and displays. All right? Number 3 says, the graph of velocity in feet per second of a car traveling on a straight road for a time between 0 and 50 included is shown above. The table values for VT at 5-second intervals of time t is shown to the right of that graph. All right, good. It's just explaining to me what I have, and that's fantastic. 3A states, during what intervals of time is the acceleration of the car positive? And give a reason for your answer. So, if I know anything about anything, wow, did you just see all the icons in the bottom tray just slide to the left? That was weird. Anyways, let's forget about our technology, which, by the way, I updated this computer, and every once in a while, something in the middle bottom pops up this box like it's recording my voice. Not the mic part, even when I don't have the mic connected. It's weird. Big Brother's watching. Anyways, let's do this. Let's go, let's start with blue. Oh, blue. Blue's a good color. There it is. So during what intervals of time is acceleration of the car positive? So the first thing we need to identify here is, how do I know what acceleration is if I only have velocity? Well, kids, we have position. I've done this before. We have velocity. And we have acceleration. Okay, these are always one derivative away from each other. Okay, and there's been times where if I have to go backward, that's an integration. All right, but we're not doing integration. No, we're just doing derivative. I am one derivative away. I have velocity. I want acceleration. Derivative is the same thing as slope. So if I look at the slope of my velocity, that will help me get some sort of indication on whether my acceleration is positive or not, if the slope is positive. All right, so they want to say during what intervals is the acceleration positive? If I want a positive acceleration, that means I want a positive slope for velocity. Positive, 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 positive. Okay, it's 0 here. Negative, 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 negative slope. 0 here. Then it's positive again. So it's positive here, because it's increasing, okay? So it looks like from 0 to 35, it's positive. Then again from 45 to 50, it's positive as well, okay? So I just want to make sure I write that and I state why I have that answer. Okay, so we're going to say between 0 and 35, and then again between 45 and 50. How come? Because slope, I almost put velocity next. Velocity is positive. These 3 dots mean therefore. Therefore, acceleration is positive. You could say is positive. You can say is greater than 0. There are a million different ways to write that. That is just one of the million. Okay? Oh boy. Did I hit the right thing? No, I didn't. Oh, I did. Your next click will be right at their line. There you go. Okay, let's get rid of this monstrosity. B. Get rid of this. B, and we'll do B in a different color. Let's go. I'm not feeling red yet this morning. It's a little too sharp. We'll do B in blue. Yeah, green. That's green, kids. Find the average acceleration of the car in feet per second between 0 and 50. Now, we just said that acceleration is the derivative of velocity, right? And we want the average, okay? So anytime we want the average derivative or the average slope, really, all I've got to do is my change in y over change in x. In this case, it's going to be my change in velocity over my change in time, okay? From 0 to 50, okay? So I take 50, subtract 0 for the bottom, because this is like, consider this like x1 and x2. Now I can go anywhere. I can look on the graph or the table. I'm just going to use the table. There you go. If this is x1, this is y1. If this right here is x2, this is y2. So my y's are going to be 72 minus 0. So I got 72 minus 0. So I end up with 72 over 50. All right, and I should probably reduce that. It looks like 2 goes into both of those. 36 over 25. Yeah, I think that's it. And let's label that. Velocity is feet per second, and acceleration is feet per second squared. There you go. A and B are done. All right? A and B are done. Let's go to C. All right, let's go to C. Okay, and let's pick another color that's not blue or green. And when I use that color, let's not call it blue again. How about that? We're going to get something a little light and fluffy. A little light and fluffy. What a soft, I just use green. Let's go orange. Orange. C, find one approximation for the acceleration of the car in feet per second squared right at time equals 40. Okay, show the computation that you used to arrive at your answer right at this point. Okay, so let's do this. I'm going to use this table again. Scroll up here. Right at time equals 40. Okay? We got to stay orange, guys. We got to do this. Right here. The key is find an approximation. We cannot find an exact thing there. Okay? There are 3 different ways you can do this. Well, I think that's 3. Okay? I'm going to take 2 of the closest points and do a change in y over change in x. So I can use 35 and 45 and sandwich them and hope that they are close enough to give me an approximation what would happen right at 40. Or I can use 35 and 40. Or I can use 40 and 45. Okay? Whatever 2 I want, all right? So like right here, look on the graph, okay? Now I'm going to change to red. If I use this dot and this dot, that will give me an approximation. It's kind of close to the slope right at 40, all right? Ooh. Or let's say I use 35 and 40, and I go I mean, I think I like the other one better. Actually, I can probably use this dot and this dot might look like it's the closest. But either one, it doesn't matter which ones you use, okay? It doesn't matter which 2 you use. Any 3 of those answers would be okay. And to me, I'm going to use 40 and 45. So all I'm going to do is do a change in y over change in x again. Okay? So I'm going to take, I'll do this down here. And I said I'd do it in orange, and by golly, we're going to go back to orange. So C, I'm going to take, changing y over changing x, 45 minus 40. And on top is 60 minus 75. So I got negative 15 over 5, which is negative 3, and they tell you in feet per second squared. You know what? I don't want to jinx myself here. But question 3 is pretty simple. It's really not that much work, question 3. Before I pick another color, let's erase all this stuff and do the fourth and final question. Wow, this is a quickie. D. We're on the last one. Approximate the integration from 0 to 50 of v of t with a Riemann sum using the midpoints of 5 subintervals of equal length. Using correct units, then explain the meaning of this integral. Okay? Okay, so let's, I'm feeling a little grayish. Feeling gray for this last. Maybe it's because, you know, it's, we're done so soon. So we're going to do great, yeah. So remember, this right here is the same thing as area under the curve. And I'm going to use midpoint in MRAM. Because a Riemann sum means we're adding up, we're going to use LRAM, RRAM, or MRAM. In this case, it's MRAM for midpoints. Okay? 5 subintervals of equal length. So look, if I go from 0 to 50, and I divide that into 5 equal parts, that means each part's going to be 10. Because 5 goes into 50 10 times. I just, you know, wanted to give you guys some simple math here. All right? So let's do this. The first one's going to go from 0 to 10. That's the first subinterval. The next one's going to go from 10 to 20. The second subinterval. 20 to 30. Okay? 30 to 40. And last but not least, 40 to 50. Okay? These are all my rectangles, so to speak, of area under the curve. Subinterval 1, subinterval 2, subinterval 3, subinterval 4, subinterval 5. All right. So let's start doing some math. I'm going to do D right here so I can see my table and keep working. The integral from 0 to 50 of v t dt. Wow, that's just unacceptable. Terrible writing. From 0, and it started with the 5 here, to 50 of vt dt. Yeah, man. Okay? So, I take the middle term of each subinterval and add it together. 12, 30, 70, 81, and 60. 12 plus 30 plus 70 plus 81 plus 60. All right, there's 100. There's 160. All right, 241. 253? Yeah, 253. 253. However, I need to take this and multiply it by the width of the subintervals. Each subinterval has a width of 10, right? So I need to multiply this times 10, which means I multiply this side times 10 as well. Sorry. It's 253 times 10. So it is 2,530. Okay? But we need correct units. What is my unit? Okay? Well, a little while ago, I said position, velocity, and acceleration, right? And this was one derivative away, okay? But backward is an integral. Okay, that's an integral. What we just did is we took the integral of velocity. So now we have position, okay? Position is simply feet, Let me explain. Position is in feet. Velocity is in feet per second. And acceleration is feet per second squared. I had this and went backward to this. Okay? So we need to put the right units. It says so right there in the problem. So let's put 2,530 feet. But then it tells us one more thing. Explain the meaning of this integral. Okay? Well, first of all, what does the graph show us again? It's a car traveling on a straight road. Okay? So if the car was traveling in feet per second in velocity, we move backward, we're just talking about the feet that the car moved, or the distance. Okay? So I would say this is the total distance the car traveled from, and let's be specific, 0 to 50 seconds. And that is a great explanation. And we're done. Look at that. That was a nice, good, simple problem. Normally these videos are taking 25, 35 minutes, depending on the complicated work that we have to do. But this one was not complicated at all. Notice I didn't grab a calculator, although I have access to one. In 1998, I don't know if they hand you the calculator and take it away from you, but this one right here, you definitely didn't need a calculator at all. I mean, maybe if you were very meticulous, you would have used your calculator to check your work you're adding, you know. Okay, check, here's subtract. It's real easy when you get tired and you're at the end of this test and you're mentally exhausted. That's when it's easy to make a mistake. So there's no shame in checking your work game, kids. I'm sorry, I was just trying to be cool by saying that. I know I'm not. I'm not. So here we go. We are done. Again, ring that bell, give me some likes, and follow me, please. Because there is no other way that I know how to let you be aware that I'm posting a new video. Okay? I'm going to start doing more so this year, focusing on the AP Calculus exams and the Algebra 2 Regents examinations for those that are in Algebra 2. So, give me a like, give me a follow, and I would like to see you for the video for question number 4. Bye-bye. Have a good one.